Okay, good morning. Let's get started. Thank you all for joining this presentation. We're hosting this webinar on PCB assembly reliability simulation. My name is Mingyao Ding, and I am the founder of Singularity Engineering. So I'm glad that you're all here to listen in. We love feedback, so if there's any questions, feel free to write it in the chat window or send me an email at info@singularityeng.com. I'll put up the email link at the end of the presentation as well. This presentation will be mostly a demonstration, but I have a couple of slides I want to go through to maybe help illustrate some of the topics we want to discuss. First, let me introduce myself and the company. Singularity Engineering is a certified ANSYS channel partner. We support the entire portfolio of ANSYS tools. Today, we're going to focus primarily on the structural mechanics portion, but obviously in electronics, the electronics cooling, fluid dynamics, as well as low and high frequency electromagnetics, things like signal integrity, RF reliability, and EMC compatibility are all important. We're also uniquely a solution partner to DfR Solutions, which produces a tool called Sherlock. This is a tool customized for electronics reliability, and today we're going to talk about how Sherlock and ANSYS Mechanical can be used together to tackle electronics reliability simulation and PCB assembly reliability analysis in particular. So maybe just to set the background, if you've seen my presentation before, I typically talk about this quite often. There are four major failure modes. This was done, the pie chart on the upper right-hand side here. This was created by the Air Force Avionics Integrity Program quite a long time ago. So these are equipment that went into aircrafts, and they found that by far the largest cause of failure was thermal cycling and thermal failure. Then there's a large segment that fails due to vibration, humidity, and dust. Today, we're going to focus primarily on the thermal and vibration side. There's a few other things we can talk about for reliability, but those consume most of the issues that people call us about. So these issues are becoming more and more important because packages are becoming thinner. Previously, we have very large DIP type of packages that are fairly robust. Nowadays, with the advent of smaller and smaller electronics devices, people like thinner and thinner packages. At the same time, sometimes boards are becoming thicker, multiple layer boards, sometimes 30, 40, or 80 layer thick boards. So when you have very thick boards and very thin components, the risk of failure increases and becomes harder to predict using your traditional design rules. ANSYS combined with DfR Solutions Sherlock provides a great set of tools for you to model and look at the entire PCB assembly. And this allows engineers to foresee and avoid reliability issues during the design process rather than through testing. Obviously, once you go through testing, it becomes very time-consuming, expensive, and nerve-wracking to try to fix boards and components and such. So the topics we're going to talk about today, we're going to start by looking at PCB assembly reliability simulation in Sherlock. I'll do a demonstration of the process of this, explain some of the details and the models we're using to predict reliability. Then we're going to look at ANSYS Mechanical and how we can integrate Sherlock and ANSYS Mechanical together. This then allows us to take an entire PCB assembly setup and perform more advanced simulations or simulations with more components. So some of the key things that my customer have found useful is adding additional parts to the analysis, having very careful control of the mesh, things like Darvaux model for solder joint reliability, and we can look at some post-processing. Finally, there's some, we can talk about some of the backgrounds in random vibe, thermal cycling, and geometry cleanup. We'll probably roll this in with the beginning section on Sherlock. So let's get started. This is Sherlock, created by DfR Solutions. And again, it's a tool designed for PCB assembly reliability. It allows you to import a wide range of layout files, ODB++, IPC 2581. These are the most common and popular generic formats, and almost every tool can import these particular formats. So let's go ahead and take a look at one of our files here. Um, let me see where I put it. Oh, right, it's on the other drive. Okay, so here's an ODB++ directory. We're going to import that in. I'll call the name. FootSense is a open source model we got that we're working with to try to improve to try to do some demonstrations of the design. So we're going to import this archive, and when we import the archive, you can see that Sherlock is automatically importing all of the layers, bringing in a part list, stack up layers, etc. And then we have a list of all kinds of analysis we can do. So if we look at the layers, um, this is the actual model itself. There's in this case, this PCB has three mounting points. We have a shape outlined in blue, and we have all of the components populated. Uh, because this is a layout file, the components are just the footprints with a record of how thick they are. And Sherlock will go ahead and build that geometry for us automatically, a clean geometry. This is a fairly simple model, probably a few dozen components, maybe 100 components. But it's very common to have boards of hundreds, if not thousands of components. And in those cases, it becomes extremely valuable to have a tool that creates this geometry cleanly for you. Let me show you an example of a board that I use often. This is a Coven board. I have done this a few YouTube videos on this board, and this is a step file that's been created uh, to go along with the layout. This is a very detailed step file. You can see we have all of the leads here. We have all of the components, but you can see that it's very common for files like this to have issues. Um, you can have, let's see, you can have some overlapping components. So there are components where we have interference areas like these. We can have, if we look carefully, some components are not touching. So we would have to define contacts between these. And obviously, there are lots of small features that we would rather not have on the model. For example, we have lots of these leads that would increase our mesh count greatly and make the simulation very slow, but they don't really add all that much to the analysis. We're not typically worried about these leads. So the first benefit of a tool like Sherlock is rather than getting a detailed CAD model, you can quickly create a model for simulation. But creating the model is just the first part. Let's take a look at the part list here. So this is a list of all the components, capacitors, diodes. We have some resistors and different packages. And DfR Sherlock automatically tries to recognize what each package is and guess what the material is. For example, capacitors here by default is set everything as alumina. We can easily change the material property from alumina to something like barium titanate, which is a more accurate model for typically today's capacitors. In order to calculate the reliability of small components, we typically don't model it in full detail. We don't model the solder ball, we don't model the leads explicitly. Instead, we take the size of the package and using various um, reliability criteria, we typically look at things like strain and deformation to characterize it. Sometimes it may not know what a part is. So for example, there's this part here, it doesn't know what it is. So what we can do is we can open up, we can try to find, let me find a browser page here. We can try to find this component. Let's see. So this is 1575AT43. Okay. So you very quickly found a component based on the part number. And this is obviously an RF antenna. and we have an example of what this looks like. So then we can go ahead and edit the part here. We can assign some material to it. For example, um, this is usually a ceramic, so we can pick one of the from a large selection of uh, of items here. We can pick a part in order to calculate the the reliability. We have to specify whether there is lead or not. A lead is, if we click on this icon here, it shows you all the different kinds of leads. These are metal structures that connects the package itself to the board, and obviously how these structures are defined, how large they are, has a huge impact on the reliability and the durability of the part. In this case, it's a surface-mounted antenna, so it's leadless, and that's all we need to do. So we have this filled in here, all the components, and we can go through some of these other ones to check in and make sure that there is indeed defined correctly. So this is a battery, and we have these are fixed round fuses. It assumes these are fuses. They may just be holes, so we may want to delete some of these things. Um, Another key benefit of DfR Solutions Sherlock is that it actually has a number of different sources for for these components. For example, if the part number here is specified correctly, you can see that there's often not very much effort put into getting the right part number. But if you have the actual part numbers, there is a global parts database where the items are validated and all of the components are pulled out, are defined properly. So first it tries to match based on the part number using this part database. If it cannot match the part number, then it has a package database. So the the layout file would have the type of package each component has, and Sherlock has at least an idea of what the package looks like. So the size of the package, the type of leads, and for example, here we have a particular package that's an encapsulant. It has a certain thickness, and the type of lead is defined. So this information may be contained. It also has we can put in a user library or AVL or pick and place library, and these orange ones are guesses. So we go through this hierarchical process of trying to guess as much as possible what the components are, so that when you run these simulations, you get to the right definition quickly. For this particular board, we have a number of components that we need to look into. But if the part numbers are specified properly, then it should be able to dig it out. So let's give that a try. So mm, okay, so we can use either a local shared global library. We want to look at the part number, and it'll go through all of these parts to try to figure out if it has these components. These are switches, so it probably won't have it, but it may have some of these other ones. Okay, so it only found one part. This part was inside of the library, so it's green in that it has confirmed the property for this particular package. So once that's done, we can take a look at the stackup. This is automatically imported from the ODB++ file. It calculates the thickness of each, and it can calculate the amount of copper in each layer, and this calculates an equivalent thermal expansion coefficient in different directions, as well as elastic properties, or orthotropic elastic material properties. The layers stack up can be modeled as separate layers or as a uniform layer with an equivalent property. Finally, we want to take a look at this one. This is pretty important. It lets us modify the geometry. Remember I mentioned that we actually create this geometry based on the layout information. We can plot different layers, for example, the first copper layer, and then we can start modifying these components. So you're not stuck with whatever Sherlock creates for you. If you see that this part shouldn't be there, this is a big connector that we don't really need. We can just delete it. And similarly, if we look carefully at some of these models, you can see that there are overlaps. Some of the components are in the ODB++ file are defined to be larger than they actually are. So we can just change the size of it. And this changing of size will automatically be applied to our simulation. So we can quickly and easily modify. It looks like this particular FB2 type of components are assumed to be much, much larger than they really are. So let's go ahead and modify it. This makes it much easier to modify the geometry and make sure that you don't have any issues. These are 3 diodes, and they're also assumed to be much larger. I'm just judging this based on the footprint on the first layer. If there is a silk screen, which there often uh, are also included, then we would see the silk screen information as well, and that typically has a bounds for how large components are. So let's skip this one, and we'll say save this, right? So when I save it, it automatically does an overlap check, and it says this part R3 overlaps another part. I can see that right here, so we can go and fix this. So this tool is really set up to quickly fix a geometry and get it ready for analysis. C14 is also overlapping, so I can filter out all the parts except C14. That's over here, and let's see where it's overlapping. It looks like this X1 component is a little too large. Maybe we'll make it something like that. Okay. Yeah, this could be the antenna actually. So, okay, so that's it for the setup. There's some components on top of our mount holes. We don't need those, so let's delete them. Okay, let's apply. Make sure nothing is overlapping. Then we can go ahead and delete some of these parts. So Sherlock is a tool that allows you to modify the model, get it prepared for analysis. It then builds a clean geometry for you, so you don't have to worry about defeaturing it. Once the model is created here, everything will be basically blocks. So if you have fancy components you want to put in, that I'll show you how to do that afterwards. But now we have a model that's cleaned up and pretty much ready to go. We can also edit. Let's in addition to the components, we can also adjust the mount points, which are these black dots. Sometimes there are many holes and some additional components may be recognized. We can put in, edit a test point, cut out, all kinds of stuff in this. But typically, go ahead from there. So once we have the model, the materials all set, we have a geometry that's clean. The next step is to assign some loads. So we can, you have the option of loading various load life cycles. Today we work with a lot of automotive companies, so we have some standardized test data for automotive systems, whether it's looking at devices put into the body cavity, door test, windshield, etc. So let's load the windshield option here. So this is a automotive test for base of the windshield. It includes a car sprung mass, random vibration profile. It includes a collision, a shock profile. We have a constant temperature, 500 hours at a constant temperature, or a pothole shock profile, as well as a temperature thermal cycling profile. So we have all of this data. You can specify how long to run this simulation for, duration, 100% duty cycle, and we want to, because this is a test environment, we want to run this for 1,000 hours, not 30 years. And once this is complete, we can go ahead and start running these simulations. We have a variety of analysis available. Like I mentioned, the ones I want to focus on are solder joint fatigue, as well as random vibrations and shock. So it'll take a few minutes to run some of these models. So I'm going to close off this particular model and open up one that's already completed. So on the solder fatigue side, we have things like tables that predict how long we get to 5% failure, so 700 hours. And if we look at the table, some of these larger resistors are the cause of low, time to failure here is set to be 2,264 hours, and we're hoping to last 1,000 hours, but some components will certainly fail before others. That's why these are highlighted in red. The rest of the components seems fine. Now let's talk about how this is done. So to run the simulation um, for solder fatigue, right, we go to Edit Properties. You specify the type of solder you're using, which thermal event you want to run, and then save and run. It'll run the simulation. The solder fatigue simulation in DfR Sherlock is based on this modified Engelmeyer model for leadless devices. This is a semi-empirical analytical approach. So what we do here is we try to determine the strain based on the geometric parameters of the device itself, as well as the difference between the temperature change, as well as the delta of thermal expansion coefficient between the device and the board. There's DfR Solutions has a lot of details on how this is done, but the whole idea is if you have a package that's expanding less than the board, then they'll introduce some sort of strain, and based on this information, we get an estimate of what that strain is. Once we have the strain range, then we can use this value to try to calculate. Oh, then the next thing we want to do is calculate the shear force applied at the solder joints. We know for a leadless device like a resistor or capacitor, there's basically two large solder joints. We know how big the solder joints are. So we put all of that information in, again, delta T and delta alpha. So this is difference in temperature from low to high, as well as the difference in thermal expansion coefficient. Plug the rest of the information in, and we get a force that we calculate from this equation. So this is purely analytical approach of looking at solder fatigue. Once we have the strain and the force, we can calculate an estimate for the amount of work done during each one of these temperature cycles. And based on some correlations from Said at MCOR, we have an equation that tells us the number of cycles of failure. So the benefit of this technique is that it's very fast. Using purely analytical algebraic approaches, we can scan the entire board really quickly without worrying about the details of the solder, where things are cracking, what shape the solder is. By using these equations, we get a quick estimate, and it's usually sufficient for simple components. For more complex components like BGAs, I'll show you the ANSYS Darvaux method a little bit later. So that's how we do a solder fatigue calculation in Sherlock. And let me just show you how fast it is. So we can, let's clear the results here, and we'll just run it again. There's a little task monitor to show you what it's doing. Oh, it's already done. So it regenerates this table. So the algebraic method is very quick. And that applies to solder fatigue. The other simulations like random vibrations and mechanical shock, these are actually full finite element methods. So we have the option to generate a 3D model, view 3D result, and even export an FEA model. So for random vibe, mechanical shock, and modal analysis and harmonic vibrations, these require full finite element simulation, so they do take some time. On small boards like this, the vibration with 3 mount points and fairly large components, the vibration is not going to cause any sorts of failure. So random vibrations, mechanical shock, both pass with flying colors. But we can take a look at how the calculation is done in this case. So for vibrations analysis, vibration and shock analysis, we typically all look at the data comes from Steinberg. David Steinberg, many years ago, did a large amount of testing and found equations that correlates to how long a particular component, how little deformation a particular component can withstand before they fail. So his criteria was 20 million stress reversals under random vibrations conditions. And he found that if the displacement is below the Z value, and the Z value is a function of the length of the component, the board thickness, and some coefficient for the type of component, and a little multiplier. As long as the amount of displacement of each package is below this value, it can withstand 20 million stress reversals. So this is one of those first efforts to quantify how reliable different components are. We can then use the Baskin's equation, so we can convert the displacement limit to a strain limit, and this is what's done in Sherlock. And once you convert it into a strain limit, we can use the Baskin equation to go from this 20 million stress reversal to a number of cycles of failure from FEA analysis. And what DfR Sherlock does is that instead of doing this conversion, we calculate the strain directly. And based on these coefficients, we can then calculate the number of cycles to failure. So for random vibrations analysis, in DfR solutions, it uses the Steinberg data, and I think there's small modifications to it to calculate number of cycles to failure. For shock analysis, we also use Steinberg data. So there's a plot of maximum allowable strain and strain rates. So and we have all of these different lines governing the thickness of the PCB, as well as this PWB, which is the maximum principal strain measured immediately adjacent to the corner solder joints. So it's like a diagonal distance of a solder and of the component and what the strain is. So if we have the strain on a board and we have the strain rates, then we can look on this graph to see where it falls, and we know how thick the PCB is. We can figure out exactly where, if the components falls, and whether it can withstand a certain level of shock. In order to get the maximum allowable strain as well as the strain rate, we need to do a transient analysis. So that's what Sherlock does, and this is perhaps one of the most time-consuming simulations. It does a time domain implicit transient simulation of the board as it undergoes a shock profile in order to calculate the strain rate and the maximum allowable and the maximum principal strain. Then it compares to this data to see whether it will fail. Using similar techniques as before, instead of having just a pass or fail criterion, we can come up with a number of cycles to failure. Okay. All right, so that's an overview of what we can do in DfR Sherlock. The ones I focus on, obviously, are solder fatigue, random vibrations, and mechanical shock. But there's obviously a lot of other capabilities. We have a conductive anode filament failure option. We have a through-hole plated through-hole failure option. We have thermal derating, thermomechanical, durability, fatigue rate, DFMEA. So a lot of different additional simulation capabilities are available. Many of these are empirical based instead of simulation based. The most simulation focused ones are shock, random vibe, natural frequency, and harmonic analysis. If you have any questions on any of these, feel free to contact myself or the Singularity team. There's also a great set of tutorials and guides that helps you go through all of these different types of simulation classes. So, conductive anode filament, we have a PTH, plated through-hole failure, fatigue, and there is documentation to describe exactly what the process is to calculate this. So there's nothing hidden about these models. Everything is documented, and you're welcome to look through it. The benefit of Sherlock is that everything gets wrapped up in a single package, and you can quickly get your simulations running, even on components with hundreds or thousands of parts. Now, so far, we focused primarily on the PCB itself. So if we look at the layer, this is the extent of our analysis. Many of my customers or ANSYS users have other things they want to add to the analysis. Maybe a housing, maybe mounts, maybe some sort of RF shielding or brackets and structures like that. That information is typically not included in a PCB assembly. So what we can do is we can export this model to a to ANSYS Workbench for analysis. So let's do this. So what this will do, and we actually don't need this to be meshed, is we'll write out a Workbench journal file. So let me show you the process of how this is done. Let's try that again. I wanted to do this. Change the name to FootSense1. Okay. So it tries to open it, but Workbench journal files are not open by default. So let's go into ANSYS Workbench. So this is ANSYS Workbench. We can go to scripting and run a scripting file. And let's go ahead and find our FootSense. This is the previous one I did, so let's go to our new one. This is the one I just generated. So Workbench Journal is a script file. It imports and it creates an engineering data for us. So this has all of the materials that we need in our simulation. We have our PCB material. We have aluminum, barium titanate, ferrite, nylon, and everything else we would need. It brings in a geometry. So let's edit this in Design Modeler. We have to edit this in Design Modeler right now because we need to keep the names consistent for the next step. So this is our Design Modeler import. You can see we brought the geometry in. We have a few of these extraneous parts that I didn't suppress before, so I'm going to suppress them now. And you can see that this is a perfectly created, perfectly clean PCB model, right? If this was a 2,000 part assembly, this will save you an enormous amount of time to create. But here we got it all, and it has all the names for the components and the PCB. PCB here is modeled as a single layer. You have the option for modeling as multiple layers, or do things like trace mapping, which will give you additional fidelity. So then let's hook up a modal analysis to this and run the simulation. Yeah, this is my modal analysis. As all ANSYS users know, right, by default, we have structural steel assigned to everything. Again, if I have a 2,000 part assembly, assigning all the components carefully takes a lot of time. So with DfR Sherlock, we can just run a macro. That's not it. Try that again. The macro is created alongside everything else. So let's go to where I put this. Yeah, put it in here. So this is it creates a Python macro that goes and automatically assigns the materials based on the name of each component. It will assign the right material property to each part. So it takes a couple minutes, and then it says material and name selection assignment completed. You can see we have the capacitors assigned as barium titanate. We got some epoxy encapsulants, copper for other components, alumina for our resistors, and some of the other components assigned as well. Now we're in the ANSYS environment. We can easily create let's do a real quick modal analysis of this. Do a fixed support, and we can just go ahead and solve it. So ANSYS mechanical take it take care of all the contacts and connections, just as you would expect. You can certainly adjust contacts. Some of these contacts may be a little bit too close, so it will define additional contacts. But notice that once we fix the model, we don't have any issues with overlapping geometry. We didn't have to do any additional geometry cleanup. So here we have the first mode, second mode, third mode. Right, so this is setting up a simulation very quickly with all of the components on board. If I wanted to, I can go in and define additional mesh controls for ANSYS. For example, right now my board is a single layer, so it's pretty easy in ANSYS to select this component. We'll do a sweep with 3 layers. Let's do a clear. And ANSYS takes advantage of its parallel meshing capability, right? So now we have 3 layers across the PCB. We could go and adjust some of these other components as well. ANSYS is known for being very efficient for modal analysis. So although I have quite a few components here, mesh elements, it does a great job. Let's solve this one more time. Okay. So the results look similar. Maybe the resonant frequency changed slightly during the analysis. With ANSYS now, we can, this opens up the possibility of doing a wide range of analysis. We can, for example, do transient simulation. We can do harmonic analysis. We can do random vibrations. The random vibrations analysis in Sherlock requires that we perform a harmonic response first, and then it calculates durability later on. Looks like it ran into a little issue here. Let's see if it'll update. So the next section I want to talk about, so that's the DfR, the PCBA reliability using Sherlock. Again, the key features here is that from a layout, you can get a geometry and material set up very quickly in Sherlock. We have models that can be cleaned up inside Sherlock itself. Then we can perform thermal cycling and random vibrations analysis. On the ANSYS side, we have Sherlock ANSYS integration. Let's see where we are here. Okay. And I've shown you how to bring models from Sherlock into ANSYS. You can also do the reverse. So if I attach a harmonic response analysis to this, and we do a frequency sweep of acceleration, let's say. So we have this model. We have to run the modal analysis again to write out the right results. But let's say we do a frequency sweep from 20 to 2000 hertz. And since this is a modal superposition analysis, we can cluster our results. For damping, we want to assign the same damping ratio as Sherlock is doing. So if you look into Sherlock, for the random vibe analysis, oops, right-click, edit here. It has a damping modifier of 0.2, so we put that information into the ANSYS simulation. And then let's put in an inertial load of in the z-axis of 1 meter squared per second. Solve that. So once we have this data set, we can bring the results back into Sherlock and use Sherlock as a post-processing tool to evaluate each component and figure out whether what the likelihood of failure is for each component or the reliability of each component. Again, if you have a few thousand components, doing that by hand is pretty tedious. But here we can plot the strain information on the board. Oh, it's I didn't choose to put the strain information, so let's look at the deformation instead. All right. So as we would expect, we're exciting the first mode at 2000 hertz. We can, with ANSYS, we can do frequency response. So we can look at the z-axis deformation. Right. So it primarily gets excited at this one mode here around 1000 hertz. That would be the first mode in the modal analysis, right? 968 hertz. So from there, if we go back to Sherlock, and we edit this model, instead of generating the results, we can import the results. So once we set the solver to ANSYS, and to do that, we can go up to here, FEA settings. I set this to the ANSYS solver. We can switch our results to imported, and now I can import the modal file, the random vibrations or harmonic file, as well as the result, save and run, and it'll do a post-processing for us. So this then allows us to use Sherlock as a pre and post-processing tool for PCB specifically, while using ANSYS to do more detailed analysis. One of the things that many people is interested in doing is adding additional components. Many of my customers have small devices that are mounted in specific ways and have other components on top. So with ANSYS, I can just import an external geometry file. And now I have a frame and I have a heatsink on top of the analysis. Because all of the components are kept, the component names are kept in Design Modeler, I can go back to my simulation now. And I can say, well, instead of analyzing as a bare PCB, I'm actually going to do an analysis with a heatsink and a frame, and maybe get rid of the other components. So let's find our components here. We'll say the frame is made of steel, and I'll have the heatsink made of, let's do copper. Probably should be aluminum. Um, now, the fixed support, we'll put that on the frame itself. So this is possibly a design iteration we want to try to see if we can get rid of the screws on the board itself. And all of the other components have material properties already assigned. So it's easy to modify the geometry, check the amount of deflection, as well as the resonant frequencies. So now we're, instead of 600 hertz, about 1000 hertz, our first resonant frequency is 3000 hertz. So our structure is now much, much stiffer. It's heavier because we added a steel frame to it. But now it's much more resilient to shock and hopefully other behavior. We can do thermal analysis and things like that. So I've shown you how Sherlock and ANSYS is integrated, how to add additional parts, how to control the mesh. One of the things that we've been doing a long time at ANSYS is using more advanced solder joint reliability models. So if we look into this, whereas Sherlock's solder fatigue model is great for looking at large amounts of components and at a very global level and understanding which small component or which large component is at risk of failure due to solder joint fatigue. At ANSYS, we typically took a very, very detailed approach to looking at solder joint reliability. First, it was noticed by Robert Darvaux that solder behaves in a viscoplastic manner, right? As you apply load to it and heat it up, it'll tend to flow and creep. And it was found that using the Anand viscoplasticity model for solder, we can get pretty good behavior or description of how the solder behaved over time. So this is a rate-dependent permanent deformation of solder that's captured in this advanced material model that's available in ANSYS. From there, there's this process of predicting solder joint failure. These are often done by packaging companies. Companies are very interested in making sure that the chip, usually large BGA chips they produce, have a sufficient thermal cycling tolerance so that it doesn't break prematurely. The life prediction goes like this. You first conduct some thermal cycling. So you have a chip or a series of chips, and you do various thermal cycling for it, whether it's minus 55 to 125 or 15 to 75. With a series of different chips, geometry, and solder, you can then, in this case, slice open the solder and track how far the crack has grown over how many cycles. So, get a big batch of packages, start cycling them, and periodically pull some out, cut it open, and see how far the crack has grown. This was what Robert Darboux did at Amcor to describe this particular process. Once you have this data, we can then simulate these packages in ANSYS. So we can do a series of simulation at different temperature cycles, at different number of cycles, and we can correlate the amount of strain energy is that builds up at the solder joints to the rate of crack growth. And you can see that the match is pretty nice when you do a curve fitting for these models. And this is perhaps some of the most accurate simulation today because it captures the nonlinear effects of the solder itself. The model is modeled in detail, so the fitting is correspondingly accurate. The model available in Sherlock is similar to this, but the error bound will be larger because you're using a much more algebraic approach. You're not capturing the detailed physics of it. But this particular approach is not really scalable. You can't model a whole board with thousands of components all in this level of detail, and I'll show you why. Oh, so this is another way of curve fitting. So Saeed, as mentioned earlier in the Sherlock presentation, did a different type. I think this is Saeed. He could be somebody else. This person did another curve fitting where instead of cutting it open, which is very time consuming, this person just looked at the time to failure. So we have mean life in number of cycles versus accumulated energy for a couple of different accumulated creep strain and creep energy density. They all kind of fit along these lines. Once you have these coefficients, you can predict the number of cycles to failure. What Darboux did here that's really special is that he figured out when the crack started, how many cycles it took for the crack to start, and the growth rate. With this two pieces of data, then it becomes much easier if your solder size change to predict how long until failure. With this approach, you kind of just know for a particular size of solder ball how long it takes to fail, so you don't have that growth rate information in the data. So back onto why this method is really only used for large components and not on a full board level simulation. We know that cracks on solder balls will occur at the interface between the package and the ball, or between the PCB and the ball. So this is a fracture mechanics problem in that the crack will grow right or near the edge, and this is typically not sufficiently we don't model the crack explicitly. What we do in Darboux method is we slice off a little piece of the solder ball, 15 thousandths of an inch in this case, and we look at the energy release rate or the accumulated energy work done, nonlinear plastic work done in this region itself. If you make this slice a bit larger, obviously when we accumulate the strain rate in this entire area, it's a little bit different. Most of the strain rate will occur right at the corner. So if you are off by a little bit, it's usually okay. But if you have too much of the solder involved, then you could have vastly different results. So it's important to set up these models very carefully in that you want to slice off a little bit and capture the strain rate in just that area. Then we have to do a nonlinear viscoplastic material model. This will take, because it's nonlinear, it'll take multiple iterations to solve. So the simulation time increases. Because we're slicing off a little bit of the solder ball, our mesh count increases, so the simulation becomes larger, and we have to model a certain number of cycles. Each time we cycle we do a temperature cycling, the amount there'll be some amount of permanent deformation in this area of interest, in the crack propagation area. And if we plot that, it looks something like this. The idea is that after 3 cycles, the amount of change stabilizes, so that from then on, each cycle you get the same amount of change, and over time, then that allows you to, which means we can stop at 2 or 3 cycles of the temperature analysis. So we're actually modeling this simulation for 7,500 seconds, and we're using a nonlinear model, and we have an extremely detailed mesh of the area. So what this means is that for these models are large. We have customers that's looking at packages with thousands of solder balls. They model all of the solder balls in detail and track this, so it becomes a fairly large simulation. And at that scale, if you have an entire PCB with multiple packages and thousands of resistors and capacitors, setting up a simulation to this extent would be very cumbersome. Which is why this is really good for detailed analysis of individual packages, and Sherlock is a great way of scanning the rest of the board to see if there are any other issues you should be worried about. There's some information on number of cycles to failure calculation. So let's take a look at the actual model here. This is the Darvaux model. I'll put this on our website, so if anyone's interested, you can download this model and take a look at it. This is a quarter symmetric model, so you can see this package is actually a quarter of the entire package. This is to reduce the computational cost. You can also do a 1/8 symmetric model. You can model. I've seen people do different levels of detail in terms of capturing the copper underneath and above to do this. But the Darvaux model in the paper was fairly straightforward. It's just a silicon, a PCB, and a solder. You can see that the area of interest of crack growth is has been sliced off, so we can zoom into those areas. And over here, we have the simulation itself. So the simulation itself, we have a static structural analysis. The analysis has 15 steps, and we have various types of thermal cycling. So this is minus 55 to plus 125. And we're simulating, in this case, 2,390 seconds. We assign a thermal condition. So this is usually the result of putting a package like this in the oven. So the temperature heat up is uniform. Right? We heat it up, hold it for a certain amount of time, drop the temperature down. We have just a single fixed support in the center here to prevent rigid body motion. And then you can see that as we heat it up and cool it down, it goes through this process of thermal cycling. What's more interesting is the nonlinear plastic work on this model. So we want to focus on just a few components, and you can see that. Let's reduce the scaling. Oh, let's do this. You can see that there's permanent deformation in this particular layer of the ball. In the Darvaux method, they actually divided up this area into 3 layers to capture the nonlinear plastic work change even more carefully. I have another model that goes through that process, but you can see the accumulation. This is kind of fast and moving very rapidly. Let's do this. So you can see the buildup at this corner of the package, buildup of the strain rate here. The last bit of this is calculating, once you know the amount of plastic strain, there's an average plastic strain. We want the integral of it, so that previously we used a command snippet, which is what's shown here, that allows you to select a component, calculate the difference between one cycle and another of the plastic strain, and you can see that they kind of stabilize to a single value. From 2 to 1, the difference, and then from 3 to 2, it's very close, so we assume that it's stabilized. Today, there is a nice little solder joint reliability ACT extension on the App Store at ANSYS. So the catalog.ansys.com. I think if I put in solder, it has a solder fatigue prediction. So this is using the Darboux method. Instead of putting in a command, you can download this and use the extension to calculate number of cycles to failure and such. And I think we should wrap up because my time is almost up. If you have any questions, and I don't get to it today, please feel free to email us at info@singularityeng.com. We love to chat with you and help in whatever way possible. We do support the Northern California area, so if you're local, reach out to us. We can provide you with guidance and consulting as well as software for either ANSYS or DfR Sherlock solutions. If you're elsewhere, we'd love to chat and help as well. So please get in touch if you have questions. I think there is a question uh, on the YouTube channel. Right. So the question is, what temperature will be the stress-free temperature, room temperature or the solder reflow temperature? Um, that's an interesting question. We have done a lot of work on solder reflow as well, mostly dealing with solder reflow warpage, but we don't have a lot of data. So the data we have is from the Darboux testing, and that was set, I believe, the free condition was room temperature. Uh, Obviously, if you're doing solder reflow, solder will start to harden at its cooling point or its solidification point, and then it slowly strengthens as it cools down. Um, but I think it's pretty typical to use the room temperature as a free condition. That's something that we can discuss in detail if you want. Um, all right, so that's definitely, we're at the top of hour. I want to thank everyone for joining this presentation, and hopefully you found it useful. And we'd love to talk to you if you have any additional questions. Thank you, and have a good day.